Okay, assuming you've already studied some proton NMR, let's turn our attention now to carbon-13 NMR. Carbon-13 NMR is a little bit easier to look at, but at the same time gives you less information. So, with carbon-13 NMR, normally we're going to be looking at the broadband decoupled spectrum. That just means that any carbon-hydrogen J coupling we're going to ignore. We're going to make our instrument not look at any of that coupling. There's things we can do on the instrument to do that. So that means that each carbon peak is going to be a singlet. We're only looking at the carbons. We're not looking at protons at all. We're only looking at the carbon atoms, and each peak will be a singlet. No multiplets here. And for carbon-13, we're going to mainly look at the chemical shift values. And something to note, recall the chemical shift values for proton NMR tend to run from 0 to 10 ppm. Carbon-13 runs 0 to 200 ppm. So if we look at this, here's an example of proton chemical shift ranges, 0 to 10. And we're going back to look at proton just to show how we've got carbonyls, aldehydes, carbonyl compound, aldehyde here, close to 10, aromatics around 8, on the left-hand side. In the middle, we've got, well, not too much. To the left of the middle is double bonds, hydrogens on carbon and double bonds. To the right, around 4, we've got hydrogens on carbons next to alcohols and ethers, oxygen-containing compounds. And then you have your halogens, amines, aromatics, carbonyls, and then your saturated stuff over here. And that's proton. When we look at carbon, we're going to see very similar ranges. Now it goes from 0 to 200, but here on the left-hand side are our carbonyls. If your carbon is part of a carbonyl group, aldehyde, ketone, ester, carboxylic acid, it's going to be down on the left-hand side. And then here's the middle of the spectrum. To the left of the middle here is your aromatics and your double bonds, kind of just like we saw with the proton spectra, chemical shift values. Then note around here, to the right of the middle, we've got our alcohols and our ethers, carbons bonded to oxygen and stuff like that. The one main issue is saturated alkanes for carbon-13 spectrum is fairly wide range. So all of your carbon-chlorine bonds, your carbon-bromines, those carbons involved in aromatic compounds, not carbon in the aromatic compound, but a carbon bonded to a benzene ring, and carbon bonded to a carbonyls, all kind of occur down here in the saturated alkane range. So with carbon-13, mainly we're going to be looking at these chemical shifts. Something else that we can look at, though, we can look at the size of the peak. But this is just very, very in general. You cannot make very strong arguments based on peak size, but you can kind of say, oh, this is leading me to believe this. Based on the height of this peak, that leads me to believe that this is the case. Let me explore that further. Let me find more data to confirm it. Because CH3, CH2, methylenes, and methyl groups, the carbon in the C13 spectrum tends to be about the same size, same height of the peak. If you have a methine, a CH, a carbon with only one hydrogen attached to it, you find that this carbon peak height tends to be a little smaller. Not all the time. And it might just be a little smaller. Sometimes it's a lot smaller. But you just can say, oh, here's a decent sized peak, but it's a little bit smaller. Perhaps it's a CH. And what we do see, though, is carbons with no hydrogens on them do tend to be smaller peaks. Sometimes half the size of a CH peak, sometimes a quarter of the size of a CH3, CH2 peak. So, but again, this is just kind of, well, they tend to be smaller. All right. Which means what we can say then is if we have a carbon-13 spectrum, the CH2s and the CH3s tend to set the rough peak height. So that'll give us roughly the height of the peaks should be. And if you see smaller peaks, you might be thinking, okay, CHs are quaternary. The other thing to look at, if you see any peaks that are much larger, much greater than these set by the CH2s and the CH3s, which tend to be in the saturated alkane range, You can start looking, maybe we have some symmetry in our molecule, because a peak that has more than one carbon due to symmetry, if there's two carbons causing that signal and they're related by symmetry, so it comes at the same chemical shift value, then you would expect that peak to be about twice as big as another peak. Okay. So let's look at an example of this, and this is in the Smith textbook. Look right here, 14.68. We have compound has a molecular formula C5H9ClO2, and here's its proton spectrum right here. Here's its carbon-13 spectrum. And when you go through this problem, what we see is when we're looking at the carbon-13 spectrum here, what do we notice? Okay, here's our saturated alkane range right here, 40 to 0. And so we say these are probably setting our peak height. And all these two peaks, this peak, are all roughly the same height here. And as we go this way, notice this peak is smaller. It's definitely smaller than the other peaks here. And notice chemical shift value. It's about 172 parts per million. Well, based off chemical shift tables, what comes down at 170 parts per million? Well, chemical shift says down here, that's carbons bonded to, our carbonyl carbons come down here. So we'd expect that there is a carbonyl in this molecule based off this one peak here. Note, if you study the proton spectrum, there's nothing that indicates carbonyl in this spectrum. There's nothing that says right away, oh, I've got a carbonyl double bond oxygen, because this is just protons. There's only the proton being shown here. Well, we can say for sure with no peak way down here at about 9 or 10 ppm, we know that it's not an aldehyde, because a hydrogen on an aldehyde, the carbon of the double bond, would come way down here. But this tells us nothing about a carbonyl. The C13 just gives us, okay, here is the carbonyl peak right here. And if you work out this problem, if you were just had this formula in this problem, you could pick out lots of the pieces of the molecule. But without knowing the carbonyl, you would be a little bit flummoxed. Knowing the carbonyl is there, it allows you to completely solve this molecule fairly straightforwardly. Note an IR spectrum would do the same. An IR would do the same, show a carbonyl, but C13 also shows a carbonyl. So work on this problem, see what you get. If you have any questions, come to see me in lab or whatever, and I can tell you, yeah, that's right or that's wrong, but see if you can get the right structure of this molecule. All right. So carbon-13, though, has its limitations. As you can see, it's not nearly as good as proton NMR for solving structures, but it does give you information that protons NMR can't give you because it's looking at carbons. And so then with the advance of NMR, people start doing crazier experiments, more interesting experiments. And one of the more interesting ones, the ones we're going to do, because our instrument will do it, is C13 DEPT. And DEPT stands for distortionless enhancement by polarization transfer. You do not need to know that, just know DEPT. The DEPT is a series of usually 3 carbon-13 spectra, but they're done in such a way to give some very interesting information. So, what the DEPT spectrum usually consists of is a DEPT 135 spectrum, a DEPT 90 spectrum, and a DEPT 45 spectrum. This is a little crowded in here. Sorry about that. And so if we look down here, I've just drawn, this would be our normal carbon-13 broadband spectrum. And let's say we had 1, 2, 3, 4, 5, 6 peaks in there. And this is our normal carbon-13. And what could we say about my molecule here just by looking at this carbon-13 NMR? Well, we could say one thing, there's a carbonyl in there. And, well, this guy's down, what is that? Okay, halfway between 100 and 0 is 50. This is about 60 to 70. I bet there's an oxygen in there. I bet this is a carbon bonded to oxygen. And then this is all saturated. And so that's about all we could say with a normal carbon-13. Without any more information, we can say, yes, carbonyl, most likely carbon bonded to oxygen, and 1, 2, 3, 4, 5, 6 carbons. We can say that. The DEPT 45 spectrum is just like the normal carbon-13 spectrum, except it does not show quaternary carbons. It does not show carbons with no hydrogens on it. So when we look at this DEPT 45 spectrum compared to our normal carbon-13, we see it's missing this peak. And because our DEPT 45 is missing that peak, we know that this peak here must be a quaternary carbon. So that tells us this carbon is a carbonyl due to chemical shift, and it's quaternary, which means there's no hydrogens on it, which means it cannot be an aldehyde. So this is the carbonyl of a ketone or carboxylic acid or ester, or maybe acid chloride or something along those lines. We know it's not an aldehyde. So right away, that DEPT 45 gave us a little bit more information. The next carbon-13 spectrum is the DEPT 90 spectrum. An interesting thing about a DEPT 90 spectrum, it only shows carbons that have one hydrogen bonded to it. If you have a CH, a methine group, carbon with only one hydrogen bonded to it, you will get a peak in the carbon-13 DEPT 90. You'll get a peak in the DEPT 90 spectrum. And so when we're looking at the DEPT 90, that shows us that this peak right here, look, if we're looking at this line, there's only one peak. This peak right here is coming up from that line. So that tells us this signal is a CH. And note, if you look, all the signals line up. The fact that this peak right here lines up directly with this peak right here in the DEPT 45 and lines up directly with this peak in the carbon-13, we are looking at this middle signal of these three right here. It's the middle one because that's the only one that lines up. All right, but we now know that's a CH. Probably the most important spectrum, and a lot of people only run the DEPT 135 because that gives us the most information. A DEPT 135 has CHs and CH3s going up like normal, but a CH2 will go down. A CH2 will come down hang down off the line. So when we look at this, we can see as we come along, here is a peak hanging down. This peak right here on the DEPT 135 comes down, therefore we know it's a CH2. The next one's hanging down. We know that's a CH2. This one was going up. And so since it's going up, it's either a CH or a 3. The fact that it was in the DEPT 90 tells us it's a CH, because only CHs show up in DEPT 90. The next one is hanging down, it's a CH2, and the last one is going up, so it's either a CH or a CH3. It was not in the DEPT 90. So if you have a peak that's going up in the DEPT 135 but is not present in the DEPT 90, that tells us that that's a CH3. So now you can see with DEPT, we can take our carbon-13 spectrum, which gives us a limited bit of information, and really get a whole lot of information. We can now know of our 6 carbons, we've got a carbonyl that's quaternary, we've got 3 CH2s, a CH, and a CH3. And now we're well on our way to figuring out the structure of our molecule. So just real quick, here's DEPT spectrum that I found online here. Let's take a look at this. A little tough to see on the screen of the camera, but look at this guy here. And okay, what can you tell me about this DEPT spectrum? What can we see? Note that this is the DEPT 45 on the bottom. The DEPT 45 is on the bottom, the DEPT 90 is here, and the DEPT 135 is right here. The normal carbon-13 is not shown. And so when we look at this, note the bottom is the DEPT 45, and it contains everything but the quaternary carbon. So this contains all of the carbons in our spectrum except for quaternary. All the carbons in our molecule except for quaternary carbons. So if I had the normal broadband decoupled carbon-13, I could pick out the quaternary carbons. Next line up is the DEPT 90. What does the DEPT 90 show? That shows only CHs. So what can we see? Okay, there's a CH right there. Here are 2 CHs right there. And note, we know this is a CH. We know these two are both CHs also because they're in the depth 90. Can you see how these two peaks are about twice as big as this peak? If they're both CHs, they should both be roughly the same size. The fact, or if all three of them are CHs, all three of them should be roughly the same size. The fact that these two are much larger than this one leads me to believe, now you can't say for sure, but it leads me to believe that there's symmetry in the molecule and that each one of these two peaks represents two carbons. So I believe there are 4 carbons represented by these two peaks, 1 carbon represented by this one peak here. Since they are all CHs, therefore should all be roughly the same height. Okay. Note that there's no other peak in there, so that tells me this one and these two are not CHs. You'll note, see how there's a little spud of a peak right there, a little bit right there, a little bit here, a little bit there. We call these artifacts. These are just residual signals because the instrument that took these spectra could not completely cancel out these peaks like it was supposed to. So you'll often see tiny little peaks in line with our other peaks, and those do not indicate CHs. Those are just tiny little artifacts. All right, now we get to depth 135. Okay, note that these 3 are all up. Well, we knew they were CHs. Remember depth 135, CHs and CH3s are up, CH2s are down. These are CHs, we knew that already, but when we come to the next one, it's hanging down. This is a CH2. The next one is hanging down, it's a CH2. The next one is up, which means it's either a CH or a CH3. The fact that it's not in the depth 90 means that this is a CH3. So now we can go through these and we know, okay, CH, 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 CH2, CH2, CH3. And that's how you analyze the depth spectra. Of course, chemical shifts do apply because this is carbon-13. Depth spectra are carbon-13. So the chemical shifts right here at about 130 ppm tells me this is probably aromatic. These carbons are probably part of a benzene ring, a phenyl ring. This one peak right here is about 65 or so. Well, what pulls a carbon down a chemical shift of 65 being bonded to an oxygen? I'm betting there's this carbon, which is a CH2, is bonded to an oxygen. And these are saturated alkane peaks. So there is our brief look into carbon-13 NMR and DEPT. I think you can see that adding DEPT into our carbon-13 repertoire is really going to be very helpful to us. And anytime we're in the lab and we've got a sample that's good enough to run carbon-13 NMR on it, is concentrated enough, we will run DEPT too, because that will give us so much more information.